Okay, hello, we're back. It's lovely to see some familiar faces. Welcome to Keeping It Simple. Colonel Reimagined. I don't know what we call this. It's lovely to see you all. Thanks for taking the time out of your day to join us. This is actually my first time in a Keep It Simple session. And so, Vivek, are you going to say any words, or would we
I'm
like to
happy
just
to,
dive
yeah.
right in?
The impetus behind this really was Sid, and we've really loved this. It's been a huge energizer to Kernel. What we want to do is look at very specific learning inquiries and try our best to simplify topics, concepts, ideas that otherwise might be a bit jarring. Just like today's session where there was kind of like a bit of a pre-read, a bit of preparation, and then kind of that shared context that allows us to then get together and try our best to keep a topic simple. We have quite a few sessions upcoming. We have this one on MEV and Flashbots. We have one on AI led by Dhruv Malik, who's been doing his PhD research on collaborative agents. We have another session with Andy on AO, um, one on DAO patterns with the metagame folks. I think we're going to reach out to Connor from Horsefax, who's now doing a lot of the DevRel at Farcaster. Have him do one there. And really any topic that feels like a topic that you yourself want to dig your teeth into, we want you to bring it up. We want you to tell us if there are any pre-reads or any people that can help us to keep that topic simple. And we want to put our collective minds behind that for the hour, try to learn it together, which has always been the main hope of Kernel, is that we might learn things together. So Andy very graciously is doing two sessions, keeping it simple with us for the next 3 or 4 weeks. This one I'm excited for, and the AO one too, has really got my attention. So looking forward to those, and maybe we just get into it.
Okay, let's go. Um, a long time ago, in a land far away, there was a bunch of nerds at a place called Cornell. And these nerds started thinking about dirty and dark things that you could do on blockchains. Leading the nerds was someone called Phil. And Phil came up with a way that you could modify the clients that was running the Ethereum network, in particular Go Ethereum. There are a bunch of different clients, but it's by far in the majority. And back in the proof of work days, you could modify your client such that if you were a miner on the network, you might reorder transactions that you saw in any block that you had won the right to mine, and reorder those transactions in a way that was most profitable to you. And Phil was like, "This is the problem." And everybody was like, Phil, here we go again, right? And the reason that they had that reaction was Phil had done a lot of really interesting work on things like dark DAOs and bribery and the kinds of collusion that you can get involved with when you begin to think outside of just the purely technical parameters of any given protocol. Start thinking about how humans actually use this stuff. All of a sudden, there's a whole area of game theory that becomes actually applicable rather than just academically interesting. And Phil, being a good academic computer scientist, was applying all of the lessons that he had learned in school to what might happen on blockchains. And of course, nobody was thinking about that kind of stuff at the level that Phil was. And so when he first proposed that it was possible that miners could order transactions in whatever way they pleased because the protocol didn't have any rules about that, and indeed couldn't have any rules about it, everybody said, yeah, Phil, pull another one. And so he did, and not only wrote a bunch of papers, but a team produced a client called mev-geth. And mev-geth was adopted by 95% of the network within a few weeks of its release because it was the incentive compatible thing to do, i.e., people could make the most profit by running mev-geth because they would order the transactions they saw in the way that was most profitable to them. This proved the case, and thus MEV, or minor extractable, sometimes called maximal extractable value, was born. There have since been lots of different flavors of this, and this is not a call about the history of MEV, but that little piece was necessary to set the scene, because a bunch of folks, including people like me, who knew Phil well and had listened to all of his talks at the various different DevCons in which he gave them, sort of still looked at this even after mev-geth and thought, I mean, like, okay, so mev-geth proves that you can reorder transactions, and that's not great, but like, hey, there's some people who are like working on it and they seem smarter than I am. And honestly, like all of the stuff that I'm interested in building on Ethereum or networks like it don't really necessarily have to do with these, sort of purely financial applications. And in fact, people like Vitalik and the others are asking us actively to build things other than financial applications on top of these networks. So like if I'm doing things like signature economies or some NFT project over here, or like weird money like Honor over there, which is not really traded in deep volumes and doesn't try to replicate the current financial infrastructure that we have in a decentralized setting, then I don't really care about this kind of stuff, because like MEV seems to only exist in like large volume trades, or when you're trying to move lots of tokens from one place to another, all this kind of stuff. And like I'm not doing any of that stuff, so like we'll let Phil solve it. That was the approach that I had for a long time. And then he wrote another paper called Clockwork Finance, and Flashbots did more work, and Proof of Stake Ethereum was launched. And we began to see the centralizing tendencies of these network effects really take hold. So you have things like Lido emerge, you have a whole bunch of side effects of what is essentially economies of scale operating around extractable value. And there are different ways of thinking about this, even within Flashbots, the organization that now exists as a result of Phil's work and others like him, because it's not just been only Phil in the years since some of his early findings. There is not exactly consensus on what MEV truly is. My own personal perspective on this, and this is a personal opinion, is that MEV is the result of the time it takes to communicate. When it takes any amount of time, any small amount of time to communicate information, the person who receives that information first has an asymmetric advantage. Right? If you know something before somebody else does, you can take action before they can. And indeed, in massively distributed networks in which there are lots of people constantly gossiping information and listening for it, if you receive information first, you can act on it most quickly, and that is often what allows you to get access to the value implicit in knowing stuff. There are other ways of characterizing MEV, but this is basically what it boils down to. So barring quantum communication, it really seems kind of impossible to solve MEV. There are ways of mitigating it, though, and that is what Flashbots and associated people tend to work on. How can we create the kind of incentive conditions that result in the most fair outcome for the broadest possible set of users, where fair is defined, generally speaking, by the largest expected payouts that you might receive is not significantly different from the average expected payout. That's a definition that comes from the chief economist of Google, if you would believe it, but it turns out to be quite useful for characterizing these kinds of really quite morally ambivalent words like fairness in a quantifiable way. So the largest expected payout is not all that different from the average expected payout. So, we've since seen lots of different flavors of MEV emerge, and the solutions that Flashbots has shipped to try and mitigate the extractable value that has resulted from increasingly more activity taking place on Ethereum and networks like it tend to have the flavor of trusted third parties, basically middleware, although again, like that's a contested term, but basically middleware that sets up trust, like a trusted third party that you would use, who promises to behave in a way that is incentive compatible for the rest of the network. A good example of this is a relay, because building blocks in proof of stake Ethereum is quite a complex task. What has happened is that people who validate blocks, who run a validator, put up the 32 ETH and run a validator on ETH, they outsource the complicated task of building blocks to other specialists, and they do so through a relay. The first relay was written by Flashbots, and indeed it was the only relay when ETH2 launched. And not long after launch, around DevCon 6 in Bogota, Flashbots relays stopped allowing transactions that were not OFAC-compliant, and that was a big sticking point in the community, as you might imagine. But Flashbots has lots of people who are based in the US, and it was important on that level to comply with what the West thinks is financial terrorism. Again, like a whole other moral conversation that we're going to avoid today. But the main solution to that from the Flashbots perspective was to open source the relay, so that any number of people can run this relay software and accept or decline whatever transactions they like. And so this is why these days you see lots of different relays being run, whether it's ultrasound money or blocks reduced to run one. They sort of kind of do, kind of don't these days. Some of the builders do. Flashbots runs their relay, and everybody does it with different rules. The nature of all of these solutions, though, is a trusted third party, because it's just easier to build, right? Like it's much easier to reason about, much easier to build a thing that sits in the middle and says, okay, like here's a relay, the validators who have the rights to create the next blocks, you can send the headers through the relay will auction off the rights to those headers to a builder. The builder with the bid that returns the most value to the validator wins the rights to build that block. They return the built block, and the relay sends the built block with the signed header back to the validator so that they can send it to the network. There's a need for a trusted third party there, because if the builder sort of builds the whole block, how do they know that sharing that the validator won't just substitute the information in that block for their own address for the Coinbase reward in that case? And similarly, there's another trust assumption on the way from the validator to the builder. I know I'm running through all of these quickly, but I want to sort of speed run this, do a demo, and then we can get into conversation. So there's a trusted third party in the middle. It's the easiest to reason about. It's certainly the easiest to build and implement from a software perspective. And it is characterized by slightly different trust assumptions than you would ordinarily see on a blockchain, which, as we are so often told, is trustless. In kernel, we tend to think it's kind of like trustworthy. But again, that's kind of a module 1 conversation that we can have over and over again. Because it doesn't seem to get into people's heads. Anyway, I won't rant about it. The main point here, and the thing that I want to focus on in this call, is that when you make slightly different trust assumptions in your infrastructure, really interesting and different things can happen. You can do all sorts of weird and wonderful stuff, which is not traditionally available on public blockchains as we know and love them today. And that is really the focus of our call. Because in thinking about all of the current solutions that exist to try and mitigate MEV, Flashbots has for a very long time proposed this concept of SUAVE. SUAVE is an acronym. Well, first of all, it's a skincare brand, which is wonderful. So if you search that, you can find it. There's lovely sort of memes that you can make out of that. But SUAVE is an acronym for the Single Unified Auction for Value Expression. Single unified auction for value expression. The idea here is that basically everything is an auction, right? Auctions, in their most abstract and essential form, trade commitments for information, right? Commitments generally have the form of payments. They don't have to be payments, but they generally are payments. And essentially, the auction is the mechanism that allows information to move from one participant to another in return for a payment or a commitment of some kind. When you conceptualize auctions like that, you begin to understand why people who work on SUAVE and on solutions to mitigate MEV are also very excited about the crossover between crypto and AI. Because in AI, it's all about how can we be sure that the data that is being put into these models and the way that they're being trained and the people who are training them and tagging the data and all of this stuff are being properly paid for the work that they do. And crypto happens to have a whole bunch of solutions for commitments, credible, on-chain, trustworthy, aka trustless commitments that can be done in a verifiable fashion in a public environment. So SUAVE has been around for a while, and it has really begun to coalesce as an implementation, not just a concept. And it takes the form of a fork of Geth, again, just like mev-geth did in the early days of proof of work. This time, what it does is it adds a whole bunch of additional precompiles to those that are available in your traditional Geth setup in the traditional EVM. So we call it the MEVM, because the modified EVM, but also MEV. So enable you to do a whole bunch of stuff that is really necessary to running auctions that are provable and that have certain verifiable properties. In this case, really, we're interested in creating auctions that have no auctioneer, right? Like, how do you create a network that does money without a trusted party? Well, you make a blockchain. How do you create an auction that has no auctioneer, that can't like peek into the bids and do all sorts of crazy things that make it incentive incompatible, or that move it away from what is called dominant strategy truth games? Well, you use a blockchain with additional precompiles, and that's what SUAVE is at a very high level. And today, what we're going to do is we're going to run through an example of how to leverage these precompiles to build a smart contract that can talk to ChatGPT. Now, is talking to ChatGPT going to solve all of our problems with MEV? No. But it is enormously cool that you can talk to ChatGPT from a contract. Is it kind of weird that you're talking to ChatGPT, which gives non-deterministic results in a supposedly deterministic environment, i.e. the EVM? Yes, it's very weird. Like, why would you want to do that? I'm not 100% sure. But it's very memeable, and you can begin to understand why it might be interesting to make different trust assumptions about your infrastructure, because they lead to the ability to do all sorts of interesting things at the application layer that are not possible with traditional blockchains. It's very easy to understand, oh, holy shit, I can call ChatGPT from inside a smart contract. I have to go through a lot of other layers of abstraction to explain why it's interesting that you might want to build blocks for a layer 2 using SUAVE, because that could act as a decentralized sequencer. I think that most of the people on this call understand most of those words. But in explaining this to like a wider audience, you have to know a lot about blockchains and a lot about rollups and a lot about how those rollup transactions are sequenced and fault proofs and all of the rest of this kind of stuff, and MEV, even in order to understand that example. So today, we're just going to call ChatGPT and we'll be like, wow, ChatGPT on a blockchain. Isn't that cool? And then, we can talk a little bit more about what these different trust assumptions at the infrastructure layer enable us to do in a slightly longer term fashion in our application level. And that's, like faster compute times, private compute, all this kind of stuff, which leads to really interesting conditions, primarily for auctions, but, possibly for a bunch of other things. So I wonder, are there any questions in the chat which I should attend to like right now, or should I just go?
I think we're good. We're good to go. We're good to go. Let's get ChatGPT on a blockchain.
Let's put ChatGPT on a blockchain. I love it. Okay. This is the music we were listening to earlier. I'll share a link in the chat. Top class stuff. If you need it, and it was shared in the prep for this call, the SUAVE docs are here. So just put in the chat. Nice. And I'm going to go straight into my terminal because that's what I want this Keep It Simple session to be about. I asked everybody prior to this call to install SUAVE. If you haven't, here's your opportunity. It should just be one line that gets you it. And as I said, SUAVE is just a fork of Geth. So you can run it, and I really want to use this command. To run it, I'm going to run SUAVE-geth. I'm going to run it with a flag that enables a local dev environment and a different flag that sort of whitelists any external call, because I'm going to be needing to call like the ChatGPT API in this particular demo. And this should just sort of start Geth. And if you've ever run Geth on your laptop before, then you kind of should be used to what you're seeing here, which is just like Geth started. And obviously it's SUAVE Geth, so it has some fancy pre-compiles, many of which we won't cover in today's call. But if you've ever like run a local DevNet, then this should not be completely unfamiliar. So that's in the background there. And then if you want to follow along, you can. After I run through the demo, I will like paste all of the steps that we take into a channel so that you have it and you can like play around with it yourself. But you know, live coding and pair coding, it could be quite fun. And it would be nice if at least one person does so, because I'm going to do this from memory and I might mess up. So, you know, if you do it with me, maybe you'll be able to figure out what's going wrong. The first thing we're going to do is we're going to make a directory for our new swap, where we're going to call ChatGPT from. Let's cd into that swap and set it up as a Git repo. The other thing that I asked everybody to do was to install Forge, which is a smart contract development toolkit. It's widely used in the industry. It's a lot of fun. I enjoy using it. And the first thing I want to do is sort of Forge install the Flashbots library, which is called SUAVE Standard. And SUAVE Standard is a smart contract library that helps use all of the pre-compiles that we built into SUAVE Geth. And Forge helps us do that. So it's just Forge install. I don't know why this fun fact is hovering over my screen. I hope you can't see it. Forge install Flashbots / SUAVE Standard. Should get you what you need. This is just gonna put in a few really nice libraries: the Forge standard test library, the Solidi library, which we already like, and then an RLP encoding library, which we're not going to use in this demo, but it's nice still to have it. The other nice thing that I'm going to do for now, just to set myself up, is make sure that the remappings, which if you've ever used Forge, then you know what these are. I'm not going to explain them in the hope that I'm keeping it simple enough here. You can just sort of remap these libraries that we installed so that they're usable in your smart contracts by writing that command. I'm going to create a source directory for my contracts, and I am going to open my code editor. So there we go. This is what it looks like in VS Code. You can use whatever code editor you like. And I'm going to make contracts, a new contract. I'm going to call it magic.sol, because why not? See? And on this external calls, which is a page here that I'll share, you will find the contract that we're going to be using today. This is the contract that will allow us to call ChatGPT from a blockchain in a 10-minute demo, hopefully. So if you come to that link, you can just copy the code back to your text editor and drop it in. While everybody does that, I will sort of very briefly run through this, because there's like just a few high-level concepts that's probably worth explaining at this point, which is that, you know, the key thing that making different trust assumptions about the infrastructure enables at the application level in the context of SUAVE is what we call kind of on-chain and off-chain compute, right? Like, how do you run a credible auction without exposing all of the transaction data that goes into it? Well, you need some kind of different programming model than exists on purely public blockchains. And so what SUAVE does is it says, okay, we have these nodes that are running in TEEs, or trusted execution environments. So generally like SGX chips made by Intel. And like SGX chips, what they do is they hide all of the stuff that they do from everybody else, including the host machine, right? So like even your kernel and everything running on the host machine cannot see what is happening on an SGX chip. So the idea here is that you can put your critical code into what is called an MR enclave, like this trusted execution environment, SGX chip, in a particular machine. It can create an attestation about what code has been put there. And then if you believe that attestation, which is a pretty low barrier in terms of like the trust assumption that you have to make, if you believe that attestation, then you can be sure that the code that you're being told is being run is indeed being run. So it's not quite the same level of assurance that you get from just like purely public smart contract code on a blockchain, but it's as close as it can be, while nevertheless making sure that there are different conditions for privacy. And the main idea here, right, is that like you can see this looks like normal Solidity. If you've ever written a smart contract, like a lot of what's going on here should be fairly familiar. But basically, what we're doing, right, is you can see there's sort of like two different parts to this contract. First, there's a register key and update the key function. And second, there's like an off-chain and on-chain function. I could have called them something more chat GPT, but I really wanted to illustrate this part of the programming model, which is that I will call this off-chain function in this demo, right? And this is where all of the heavy logic is going to happen. So I'm going to call the off-chain function with a confidential inputs, right? And that is what will get run in the trusted execution environment. After it has been run, you can see that both of these off-chain functions return a particular like bytes array that calls an on-chain function to update the state, right? So you never update states in your off-chain functions. Basically, you pass sensitive data like your bids in an auction or whatever it is that you're like bids, bundles for a block, bids in an auction, this kind of stuff. You pass it to your off-chain functions. The compute happens off-chain in a trusted execution environment. The result is returned in this line of your off-chain function, which calls some on-chain function that updates the relevant states on-chain. It doesn't leak any of like the information about what the bid was in the auction or what the bundle was in the block. It just returns the necessary information such that you can always be sure that a valid computation was run and that it was run by the correct person who you encrypted the inputs for. So this is like a different way of thinking about how to... Sorry, my Wi-Fi crashed.
Andy. No worries.
Anyway. Okay, let me get my screen share back and then we can continue. So we're in the smart contracts and discussing the programming model. And basically, like the core idea here, right, is that if you can trust the attestation provided by the trusted execution environments, then you can be sure that the code that is defined in this public smart contract is what is being run in any off-chain computation. So you still define all of the logic that must be run in a trusted execution environment on-chain, and anybody can look at this logic and say, yes, it does what I expect it to, or no, it doesn't. And we can be sure that it is being run in an environment which says it will do what it says on the tin, because we have this attestation from a TEE. So, you know, like that's the basic programming model. You can see that there are these two parts to it. I want to like be able to like register my, in this case, ChatGPT key in confidential storage, and then use that key to start a new ChatGPT contract instance and get it to like send it a prompt. And in this case, my prompt is going to be say hello world, right? And get it to complete that prompt. It's like I'm using the completions endpoint. This is one of the contracts that is coming from my SUAVE standard library that we imported earlier. You can go and take a look at that. It's in your lib under source. And then you can see it should be in protocols, ChatGPT. That's all, that's where it is. It's kind of what it looks like. So we're going to go ahead and do this so that I can illustrate a little bit of what I mean by kind of like on-chain, off-chain. Think about it in the sense that you get your off-chain functions to do all of the heavy lifting. That's where you define your logic, everything that you want to run, because that's run off-chain in a trusted execution environment. And the results of that computation are returned to an on-chain function, which updates any necessary state, if that is indeed what you want to do. For instance, there's like another example that we have where we run an auction on transactions, and in this case a user would submit their transaction to a function like this that stores it in confidential storage and then leaks transaction information about, for instance, what direction on Uniswap is being traded or what two pools on Uniswap are being traded without leaking the direction or the volume. And you can do that through like emitting logs on chain that searches then look for and then can use to backrun transactions. And you can do this, like using SUAVE to do that is a much better solution than using a trusted third party like a relay, because you can be sure that what is defined in the contract that everybody is using is what indeed is happening, because you have both the publicly verifiable code, which is what we're looking at now, and you know that it's being run in any off-chain function. It's being run in a trusted execution environment. So we have our code. Let's just call this magic. Call it chat. I don't mind. Let's build that particular contract. You can make a foundry.toml file and specify your compiler version if you know what you're doing with Forge, but there we go. It should just build well enough from the docs. And once you've built it, we can use SUAVE-geth. If you use the little convenient tool that we built in, it's called spell, and you can deploy your magic.sol file. And this is just syntax that Forge uses. You want to deploy the magic contract in the magic.sol file. There we go. That's deployed locally on my SUAVE-geth network. You can see there's the bytecode for it. Oh my gosh, beautiful. I'm sure everybody understood that. And once we've deployed it, right, now there are two steps that we need to make to interact with ChatGPT. First, we have to put our GPT key into the confidential store. And then second, we need to call the contract from our local machine, which is very exciting. Now I have a ChatGPT key. I'm going to ask you really nicely, please don't abuse it. But also it's only got, I think, like $6 on it. So if you do abuse it, like good luck. You'll probably get like a few million tokens, I think. The first thing that I'm going to do is like store that in confidential storage using this register key off-chain function. And you can see it creates a data record and it puts that in a particular place. The confidential store is just a key value store that's append only, much like a blockchain itself, but it's just a Redis database in the background on your local nodes or in a trusted execution environment if that's being run properly in production. And SUAVE-geth also comes with a way of doing that, which I was testing earlier. And so here it is. I'm going to use the spell tool again. I'm going to make a confidential request. And I'm going to pass as an input my ChatGPT key, which I will also paste in the chat. Why not? Because you can use the same key if you don't have a ChatGPT key to follow along. And I'm going to call the register key off-chain function. And if I do that, you can see there is my ChatGPT as a bytes array, my ChatGPT key as a bytes array. And I'm calling my contract, which was returned when I first deployed it to the chain. So that's great. My confidential store is working and it has my ChatGPT key in it. Now to refresh your memory, we want to call this off-chain function and have it instantiate a new GPT instance, instantiate a new message type, and then send that message to the GPT completion endpoints. And in this case, we'll have the prompt say hello world, which is great. So let's do the same thing here, which is SUAVE-geth spell conf request. Let's put the contract address. Yeah. And this case, we're going to call the off-chain function. And let's see if it works. You can see it's waiting for something. Oh my goodness. And there it is, a log emitted on-chain. You can see the transaction detail. Oh yeah, right, there's the contract. That seems to be legit. We just managed to call GPT from a blockchain. Admittedly, a local blockchain, and admittedly in a speed demo, but there it is. If you want to say, is this real? This actually might not work. Let's see. I was struggling with questions that take kind of like more than 10 seconds to get a response from the completions endpoints. So let's just run all of this again. You can deploy magic.sol. You can see it's a different address. So let's grab that. You know, we'll be working on the confidential store to make this particular part easy, because it kind of sucks that you have to store a key and then call a function. That's just the way it is at the moment. So we're storing our key in our new, in the same confidential store, but associated with the new contract. And then let's make this off-chain call this time. Is this real? Maybe. I'm sorry, I can't answer that question without more context. Can you please provide more information? So there you go. That does actually work. It's very surprising. Who knew? Live demos generally don't. But there you have it. Calling GPT from a smart contract and getting a response. And that's because we're making some slightly different trust assumptions about the infrastructure on which the stuff is running. In particular, that it's occurring in a trusted execution environment, and so we can do stuff off-chain and nevertheless still have strong trust guarantees about what is occurring. It's not quite the same sort of trust guarantees that you might expect from an ordinary EVM or public blockchain, but it is nevertheless interesting in that it allows you to build all kinds of applications that would not otherwise be possible. Most of these require using the confidential store to put sort of transactions or bundles or the sorts of things that are required both for searchers or builders. And that's primarily what we're interested in SUAVE, but this is just a demonstration of the capabilities that come along when you have this kind of setup, as opposed to just like everything is happening in a single threaded virtual machine, always public, always on chain. So there you go. Discussion.
Well done. Well done. We got it on chain. That actually is one very quick one for me, and then please, anyone else, please feel free to just unmute. That last response from GPT, is it still in the off-chain trusted environment? And if so, what does it take to then move it onto the chain? At what moment do you feel that would be? Did I get it right, first of all? Is it still in?
Yes. Yeah, absolutely. Absolutely. So I have become
Stay on video, please. That's
I have become the AI, which is exciting. But if we take a look here, right, basically like where the response is coming, it's like it's emitted in a log, right? And so like if you go and take a look at the contract, like that log is on chain, right? Like logs are not contract storage. And so you can kind of abuse them to do all sorts of things. And Vitalik actually has a long post about how logs were like the worst mistake that they made in Ethereum. And if he could go back to the beginning, he wouldn't have logs, because they're one of the reasons that state has bloated like so quickly and all the rest of it. But basically, like what's going on here, right, is that I've defined an event called response. And then in my you see here, like in the off-chain version, right? Like I first retrieve the key from the confidential store. I do some stuff to make that key usable. I instantiate a ChatGPT contract and a message type. I send the prompts to that GPT contracts using my key and all of the rest of the stuff that is set up in this file that I've imported. and then the response that I received is stored in this temporary variable called data, and I emit it as this event, right? But that off-chain function, like it can't do anything on-chain, and so it in fact just returns the name of the function that it wants to call once it's been run. In this case, it's on-chain. And there's a little modifier there, which is called emit off-chain logs. And that little modifier comes from another file that I've imported, swap.sol. And it helps you emit events in off-chain functions on-chain. And this is like a very useful pattern in general, because for instance, a user who wants to like send their transaction to SUAVE to be protected from like MEV and like sandwich bots and whatever in the public mempool can like send their transaction to a contract like this. It will put it in confidential storage and nobody will ever see it, but they can emit an event which says, hey, I've got a transaction which is trading USDC for ETH on Uniswap V2 on Optimism. It doesn't have to say the direction or the volume, but like there you go. And that's enough for a searcher. That's enough information for a searcher who's listening to the logs, the event logs from this contract, to construct all kinds of backruns and try them and submit those backruns to the same contract, also confidentially. And then the contract itself off-chain can go and like match searcher backruns with original user transactions and submit like bundles, what are called bundles, to builders to put into their blocks, and off you go, right? So this is how relays work at the moment, but this is what a relay like in a smart contract would look like, and you just kind of abuse the events and have the off-chain function call an on-chain function that emits those events, which is how we're getting this kind of results. It's definitely, it's on-chain, right? But it's an event, so that's how I get around it. Where else are we going?
I got muted, but go ahead. I think Christian, if you'd like.
Yeah, no, I was just I was curious, like, would you say one of the main I guess reasons behind SUAVE, or one of the biggest use cases that you were talking about, which, I wouldn't say I wrapped my head around all of it during this time, but I definitely I'm curious to learn more. But would you say like one of the main use cases is to make, I guess, remove the auctioneer from the auction? And if that's the case, could you like just delve into that a little bit more? Because I'm curious. A lot of use cases come to mind all over the place for that, which we can talk about more. But
yeah, auctions are everywhere once you begin looking for them, right? And the problem in a lot of them, in terms of making genuinely incentive compatible like dominant strategy truth claims, is precisely the auctioneer, because there's always issues of collusion around it. And so like one way of thinking about SUAVE is like, Anoma, who we also know, Chris and our has been like quite a big part of kernel. Anoma has this notion of kind of like a unified intents architecture, and it's like homogeneous infrastructure, heterogeneous security is kind of like the promise of their white paper. And again, it's like, how do you have a unified thing that is genuinely distributed, right? Because again, those two things are really always in tension, right? And so like you have something like the EVM, which is it's a logically centralized thing, right? Like the EVM is like one monolithic machine, but it enables a distributed network. And when you begin looking at these kinds of things, you're like, oh, okay, like this is really why like decentralization is a spectrum, and it's a multivariate spectrum, right? Because it's architectural, it's logical, it's political. There's lots of different kinds of it. And what Enoma is trying to propose, and in a similar way, what SUAVE means in terms of like a single unified auction, is you can kind of like unify the marketplace in which mechanisms can be proposed, right? So in this case, like anybody can write a smart contract that has a builder algorithm and put that on SUAVE. And then if you get like the most order flow because you have the most efficient algorithm, like props to you, right? Off you go. And so what it enables is genuine competition for efficient mechanisms. The thinking here being that there is no way in which anybody can say definitively that this is the most efficient auction, right? It's not possible. If you know anything about auction design, and it's a huge field of academic study that exists, you know, decades prior to crypto, then you will know that like there's no such thing as like the best kind of auction. And so the approach here is not to say, okay, like we can come up with like the single unified auction. It means like we have a marketplace for mechanisms in which people can propose different ways of ordering blocks or making bundles or collating data for AI, or thinking about like different funding mechanisms for tagging data, contributing data, retroactive funding, whatever it is, right? And then propose those mechanisms as contracts on SUAVE, which use the slightly different, you know, assumptions about like the infrastructure in order to build interesting applications. And in all of those cases, you'll see that like basically at like a theoretical level, what's being done is the auctioneer, the person who inevitably sits at the place closest to the information, who receives the information first, right? Because MEV is a result of the time it takes to communicate, because whoever receives information first is always at an advantage. And so like the auctioneer here means whoever receives the information first, or who has privileged role in processing that information, like they get removed, right? And the hope and the theory is that the mechanisms that do that in the most efficient manner will inevitably be the ones that are favored in the long term. I don't think that that's guaranteed, because it's enormously complex, and it has to do also with like human psychology and relationships. Because if you look at like the marketplace for MEV at the moment, it's so deeply defined by who knows whom, right? It's just like the old boys clubs of banks and stuff, right? It's like if you like know the searcher because you happen to work together somewhere, then like you get more order flow than like the next builder, and therefore your market share goes up. And it doesn't really have a huge amount to do with your capacity to write like the greatest software. It's mostly about who you know, and that kind of sucks. So this is like,
yeah, I was thinking like it a lot of what you're saying reminds me of you know, like what the internet is built on in a way. Like, and by that I mean you know, like the internet is financed mostly by ads, and that's what keeps a lot of things running, you know, because that's the revenue that enables the people to keep you know, their stuff on the internet up, and those are all run by like mainly by auctions. You know, that's what keeps the ad money coming in, and it's the exact same where like Google generally like hosts the auction and is the auctioneer. And so it's a lot of like the same problems, which I think could be harder to solve because you have to deal with people like Google, but like conceptually very similar.
You know what's hard about the Google ad auctions is the latency, right? That's really the challenging thing, because like again, these auctions can be provably more efficient, right? And like, yeah, you have to deal with Google and like the layers of bureaucracy that exist in any inevitably big organization. But like if you like have a provably better solution, then like that probably would win out in the long term. The genuine challenge with ad auctions, which is like an idea that has been like long discussed in Flashbots, is
really?
the latency requirements, right? Because like that's like you still want to have some kind of like verifiability around what's being run. In this case, like a smart contract on a EVM-like network, right? Because people recognize that as it's a legible concept, right? But in order to have consensus about what those contracts are and their current state, they need to be on like some kind of distributed network. And generally speaking, those ad auctions are, I mean, you know, right? It's like 10 to 100 milliseconds, right? When you're running a consensus, yeah, exactly. When you're running a consensus network on 10 to 100 milliseconds, then you're talking like Solana level hardware, right? So
yeah,
it's a very
one of the coolest. Yeah, and I mean way too fast for any more decentralized network, I guess. But yeah, one of the most interesting white papers I ever read was about a basically like a blockchain specifically built for that. Didn't get any traction though because like nobody in the ad tech space wants that. But yeah,
Yeah, you shared
thanks.
that with me.
Thanks,
It's a
Andy.
really cool paper. Yeah.
Oh yeah. Oh yeah, that was a while ago. But yeah, super cool. Thanks.
Question. So I kind of get freaked out by hearing about AI agents and kind of how they're even faster in terms of like arbitraging. Like I think there was a person who had a whole bunch of ETH moved over into their account to purchase an NFT, and they basically were able to arbitrage this. And so as things speed up even more and more using these AI agents that we're going to be, I'm kind of, before I didn't care really about MEV too much. I didn't have these huge transactions, but I think more and more of us are going to be targeted, right? And so it's going to make sense to have something like this, at least an understanding of how we can do this and hide our transactions. Does that make sense to you, Andy?
I think so, right? The reason that I got involved with Flashbots is primarily this, right? That I also didn't really care about MEV, and then Phil proved to me that it can destabilize consensus, right? So there's this really interesting thing that is happening as a result of both the increase of automated agents of various different kinds, and the effect that has on the individual, because you can go after much lower value transactions rather than just trying to get the highest ones with some kind of really compute heavy infrastructure that you're running, that it's only really worth going after transactions in the millions. And the collective effects that something like MEV has, which is that it destabilizes consensus, because inevitably what it results in is the most sophisticated actors are those who are able to receive information most quickly and act on it most quickly on the most consistent basis. And so those sophisticated actors tend to become more sophisticated over time and tend to accrue more money over time, and that ends up in what we would see as a negative cycle, right? Because they just become more and more sophisticated and more well resourced, and so there are these centralizing tendencies over time, which then result in imbalances of power in the network, like Lido having more than 33% or whatever it is. That's a trivial example, and then that can undermine the properties of the consensus algorithm, right? Which expects an honest third of validators in the case of Lido, but others are equally relevant to this. And that seems like a really big problem, but it's also fascinating, right? Because ultimately, and this is the great insight of people like John Dewey, for instance, is that when you have something that is both a problem for individuals that is recognized as a problem collectively, that's the impetus for genuine public goods, for the emergence of a genuine demos, right? It is the almost prerequisite for a functioning democracy, because you have a bunch of you have a public recognize itself and come together in order to solve problems that affect them as individuals, but also have these collective effects. So I think that that's kind of quite promising in some way, or at least it presents the allure of something that's really meaningful to work on, because as you say, individually, all of us will suffer from the effects of extractable value. There's no way around it. And collectively, there is this massive problem that it destabilizes consensus. and undermines the properties of the protocol that we rely upon to go on agreeing about the state of any given network. So, I think that's also always been Phil's spiel, right? If you listen to him, he's like, this is terrible and things are so broken, oh my god. But also there's it's really interesting because no one ever has been able to solve this, right? And blockchains present a context in which it is at least potentially tractable, right? It doesn't mean that we'll win. It doesn't mean that we can come up with incentive compatible mechanisms that are genuinely more efficient and that do attract more order flow than centralized builders, because there's all sorts of other considerations in the mix, like personal human relationships and other things that are very difficult to account for. But they are the only like context that has ever emerged in modern civilization, to my knowledge, in which this particular problem of who receives information first is tractable, right? Like the first MEV that we know about was in like 1834 in Paris, where like you had the stock market prices from Paris were sent out via horse cart, right? And when telegram became a thing, there were these two brothers who sat in where was it? I don't know, some French city that begins with a B. I can't remember exactly which one it was, but like basically what they did is they bribed the telegram operators in Paris and in their city to include an extra character, right? So the operators in Paris would include an extra character that said if the price of a share was up or down, and then they would delete that character, because you could do that with the telegram, right? You said like delete that character was a mistake. And then the telegram operator in their town would receive the telegram, would see the character, and would send like up or down the price signal to the two brothers, and then would delete the telegram and pass it on to the relevant person, right? Delete the character in the telegram, pass it on to the relevant person. And the horse and carriage would only arrive 3 days later with the actual stock prices from the Paris exchange. And so the brothers would like buy or sell the shares 3 days in advance, right? And off you go. Like, that's the first documented case of MEV in the world. You don't need a blockchain for it. And that kind of illustrates the point, right? Because like these sorts of things have gone on in modern financial markets all the time. That's why high frequency trading is even a thing, right? And why you want a straight line from New York to Chicago, whatever it is. So, you know, like nobody's been able to solve it. It's always been an issue. It's always been a centralizing force. It's always resulted in abuses and asymmetries of power. But here we know more about it, and like it seems a little bit more tractable. It's still like a fiendishly difficult problem to solve, and I don't think that it is solvable bar like instantaneous communication, which I'm sure will introduce its own problems. But that's kind of the way of the world, isn't it? You know, like we come up with solutions and they create more problems, and then we come up with solutions to those and they create more problems. And eventually, hopefully, we break our own mental models of solution and problem and just sort of see reality more like it is. But that's also like a whole other call.
Yeah. I know we're a bit over, so if anyone has to go, please feel free. But if you do have any final questions, anyone, especially who hasn't yet.
I'm going to jump in real quick. Can you copy those two commands for, you know, how you, I think your retrieve and store commands real quick into the chat, Andy? Yeah. Sorry about that. Whoever wants to go next.
Just change the contract address. Okay. Join us next time for more fun on a hyperparallel computer this time, which is like a whole different kettle of fish to what we've been talking about today, and also a lot of fun.
Yes.
Yeah. It'll be fun. We get to explore alternative ways of thinking about this kind of stuff.
Yes. Yes, yes, yes. That one will be on May 14th, 12 days from now. Take care, everybody. Always good to be.